So thank you very much, and I thank the organizer, Yasir, for inviting me to this wonderful conference. And so I'm not a spin liquid person. It's the students who got me into the spin liquid, presumably because of their frequent visit to ICTS and having people like Subra and all working on this. But now I'm sort of hooked up, and we believe we have some model for classical spin liquid, which we believe will have quite a bit of potential to explain it. As we sort of know that, I mean, spin liquid is more of a quantum concept, and which came from the superpositions of your various disorder and having topological degeneracy with fractional excitations. It really doesn't have those analog in classical theory. So that's why I sort of chose these keywords in the title just to confuse you more, that if you really think now in terms of a vector space of classical spin in some placket, we might be able to talk about the superpositions and not necessarily fractionalizations, but fragmentations, and may also we will be able to talk about degeneracy. So that's roughly the idea, using the groove theory constructions from the spin liquid, which, as you will see, that it's more of a generalize the earlier ideas of spin ice and few other models. So I'll start with some introductions of this, and what we are going to do is going to apply this on square Kagome lattice, and presumably that's why I'm here, so that I'm not too much off from Kagome. But I believe that or at least a bulk of the presentations will be on general constructions. And in the phase diagram, what we will find is that there will be a very narrow region of spin liquid, as long as there is no DM interaction, dissolution-schema interactions. But once we turn on any finite dissolution-schema interactions, we find that the spin liquid will be unstable to a ordering between. In fact, it comes as at the phase boundary between the ordering of vortex and anti-vortex with different topological number, and there will also be a fragmentations like or mixed state of order and disorder phase in the square, and we will also confirm our results with unbiased Monte Carlo simulations. So with that, let me start with kind of the most generic phase diagram of a spin system with nearest neighbor hopping, nearest neighbor interactions, like. And if you have strong interactions, you do have uniform phases of magnets of some order parameter with spin wave excitations. And as you go to the other limit, in which you will have the entropy to dominate the free energy, or if you have frustrations or constraint which sort of does not allow the ordering to happen, you will have paramagnet, and one subset of this paramagnetic phase would be spin liquid, spin ice, in which the frustration not only just disrupt the ordering, but also does not allow a complete disordering of the nearing spin, rather it allows some correlations between them. That's the spin liquid to me. And somewhere in between would come vortex or skyrmions, which I do not need for this talk. It's usually somewhere between the uniform and a complete non-uniform phase, in which you will have a local textures of spins. So we don't study them just for their ground state, but more than that, we study them for their excitations and having fractional excitations or the spin wave excitations, and also their dualities to other theories. Okay. So let me try to give a survey of the models of spin liquid, and I'm going to focus only on the classical one here. And to capture as many models as possible within one slide means I'm going to lose out the details, but I'll try to put them in one coherent way. Let's say we start with some nearest neighbor interactions of spin, and we do either a linear mapping or a nonlinear mapping or a multilinear mapping. So the linear mapping would be that you define some sort of a magnetizations in a placket, and we take a linear combinations of spins into that, and you do also have this local spins constraint of spin 1 at every sites that you can always put it. And the boring trivial phase would be when this M or the magnetizations will be uniform everywhere, and also there will be a easy axis of the local spin, so that will be the magnet. On the other hand, the spin liquid and spin ice, so I will not be really distinguishing between the ice and liquid. So for me, everything that is disorder with different sort of reasonably good correlation length will be the spin liquid or spin ice. So they sort of come synonymously. And the spin ice rule would be like when you have a kind of a time reversal invariant system, if you like, with the magnetizations being 0, and the local spin in some sort of a disorder configuration is also 0. But then what it does is that, and you also need, I mean, the spin rule is more embedded into this, saying that you do find magnetizations in which the Hamiltonian becomes diagonal in that placket, such that with m square being being positive, you really do want to have a magnetization to be 0 configurations. So only if you can write a Hamiltonian in a summations over the placket, with every placket having a sort of a quadratic term or eigenvalue, if you like, that's the spin rise rule. Not so. This means not all Hamiltonian would follow it. Okay, but if it follows, then what you have is that under this constraint of m equal to 0, you'll have different degenerate configurations, and that's the spin ice. And if you break the spin ice rule locally, you will have local excitations, and you will have you can write this order parameter in terms of gradient or curl of some field, and you will have monopole Coulomb phase and so on and so forth. And as I said, the caveat is that not all Hamiltonians would follow it. So especially if you have DM interactions, that sort of Hamiltonian does not follow this model. So and the other one, which is more of a more recent understanding of spin liquid, is the soft spin model, in which what you do is that you go from local spin to the global spin with a Fourier transformation, and then because of the quadratic nature of this Hamiltonian, you have a eigenvalue problem, or you have diagonalized this Hamiltonian in the momentum space. But the caveat, and then if you have a flat band, that means there is no really preferential wave vector or ordering, so that's spin liquid. So if you have a flat band at the for the spin at the lowest energy, that's the spin liquid. According to the description. But the problem here is, of course, that you have gone to the global spin, so you cannot really put back the local constraint for the classical spin. You put that constraint in the global one. And there are a few other things that you can talk about in this sort of model, but that's not going to be, I don't need those for this talk. And here is our group theory approach, which is based on these two papers. I'm not sure if any of them here. As they have used this group theory analysis for Kagome and pyrochlore, and pretty much looked into the order states. We're going to generalize those to disorder, spin liquid, and fragmented phase as well. So the idea is you can sort of think of it as sort of borrowing from what I described for spin ice, but now generalizing that. So let's say you have some lattice. Here I'm using a square Kagome, but or Kagome, but you can just think of no square Kagome, but you can think of any lattice to start with, and you take a placket which will have, so that's like a conventional unit cell, which is the one that you want to choose is also invariant under the point group symmetry. So now you have a kind of a, so let's say you have n spins here, so they will have a vector space of, if you have a spin vector in that placket of 3n dimensions, then what we do is we take the point group symmetry of that lattice, and we look into the irreducible representations, and we expand this spin as a linear superpositions of all the irreps, right? That's the undergraduate thing. And here what M does is, M is like a, which is the expansion coefficients, and these are real number, and those are the magnetization, those are the order parameter of the theory. Okay, and so the local spins are like the fragmented objects of this spin of this placket spin vector with some projections operator, which will help us to write down many of these wave functions in terms of these projections, but I will not be referring to the projections so much. So here so here you do have many constraints. One of them is the local constraint, which is easy to put, and then there is also a constraint over the placket, which is to preserve the number of spins, because in this placket I have sort of overcounted the number of spins from a primitive lattice, and that has to be taken into account, and if you need to know more, I'll tell you later. But this is the more important constraint. What it does is that even if you will be able to find a Hamiltonian which will be diagonalized in each placket, and you will have a sort of a linear summations over all the energies for each placket, but this is the constant that will correlate between different placket. So essentially that leads to, and also one more thing it will happen is that not all the E-rays or not all the order parameters will follow this constraint. So it inbuilt gives you a frustration as well as correlations between different plackets. Even if you do not have any lattice frustrations, in principle you may also have spin liquid phase because of this local constraint. Now you may say we have only used the discrete rotational symmetry. What about any continuous rotational continuous symmetry on the E-rays that remains present? And indeed there would be emergent phases, depends on the multiplicity, and I think I don't need to, but if you have any sort of n number of multiplicity of the E-rays, you will have that O times that multiplicity, because different E-rays don't talk to each other, but within one E-rays, different multiplicity talk to each other and they will have a rotational symmetry. Okay. And now I can think of writing this total spin of this entire lattice as a direct sum of this each placket spins, but I will call it constant direct sum because different plackets still talk to each other under this constraint. And any generic nearest neighbor Hamiltonian with spins, you can now break it into a direct sum of all the local placket Hamiltonian, which is quadratic, again in terms of this placket spin. And then they are diagonalized in the irreducible representations. Okay. So now what you have is that the total energy of the system becomes a summations over all the energies of each placket. So naively speaking, it looks like this entire system has just become a summations over each placket which do not talk to each other. But just to repeat the fact that this constraint does introduce correlations. Okay. And what also we are able to come up with a ground state spin vector for this entire system, which is a direct summations over the spin vector in each placket. But now we will not necessarily be able to obtain one order parameter. We will rather get an ensemble of order parameters depending on the frustration, depending on the this local constraint, which sometimes won't even allow any of this single order parameter to become the lowest energy, because if that order parameter does not satisfy this constraint, you need to have more than one order parameter to satisfy this constraint, and that will allow you an ensemble of E-rays, and that will also allow you a degeneracy in which there can be different combinations of these order parameter values with the corresponding energy that can give you some sort of a degeneracy in the theory. Okay. Let me classify these phases. So the uniform phase would be when one of these eigenvalue has the lowest energy in a given parameter space, and if that order parameter satisfy all the frustrations and constraint, you are done, you have a uniform phase, and so that's your energy. And you can also have, you might be able to get rid of the frustration or constraint in another uniform order phase in which they will be staggered. So not one order parameter, but two different order parameter, or maybe three or so, will also be ordered with a staggered way. Okay, but the spin liquid phase is what we are after, which will be a random combinations of all possible E-reps or all possible order parameter within each placket under this constraint that if it does not break primary Walser symmetry, that total magnetization has to vanish, and the total energy under all these irreducible all these magnetizations should give you a degenerate energy, which should presumably be uniform everywhere. But within each unit cell or within each placket, there will be a random combinations of all these order parameter. So now imagine that, let's say my entire system has again broken into one E-reps in which different order parameters sort of takes random values, and then you average them over and you get a spin liquid phase. In the thermodynamic limit, you can actually do the same thing in the other way, that you take one snapshot of all these order parameter, all these E-reps ensemble taking random values between different E-reps, and you take one snapshot and you take an average, and if you take the average over this entire lattice, one snapshot will give you the same energy, which will be n times this placket energy. Okay, and that will be, and the fragmented phase will of course be when there will be one order parameter which will be uniform, but it still does not satisfy the constraint or frustration. It will then get scrambled with more order parameters which can take random values, and then you will have a fragmented or mixed phase. Okay, and eventually we want to diagnose this with respect to spin correlations, which will be, we as I was preparing this talk, I realized that we can even evaluate these things analytically, but eventually we will be doing Monte Carlo simulations in which we will look into different spin correlations even in the liquid phase, and we will find also things like a pinch point and all. And my focus is going to be on square Kagome lattice because of some recent interest, and I think some of the organizers are also expert on this. So the square Kagome, I don't know if it was presented earlier, these are the materials that has been studied recently, in which the copper are the dominant orbitals for the low energy physics here, and they seem to be more of a layered system. And if you look into the top layer, any of this layer from the top view, it does have a square lattice. So there are some earlier indications of no magnetic moment down to the lowest possible temperature they could measure, and the claim was that these are spin liquid. And I think there was, especially the beginning case, that people thought that this might be a quantum spin liquid. I think that's what the models had also been. But we do have reason to believe that these coppers are not really giving you a spin half, so we'll rather take the view that these are classical classical spin liquid or not. We'll come back to it. Then there had been later studies showing some ordering at low temperature in one of the directions and disorder in the transverse directions. So this is what we call fragmented or mixed phase. And the theoretically, it's Yasir Iqbal's group has done quite a bit. So if you have any more details questions on this, ask him. And their first study was on quantum spin on Heisenberg model on this lattice, and they found valence bound solid. And I think there was another study later on, they found spin liquid. And once you put a magnetic field, then there are some magnetization plateaus, and I think Yasir also did some classical spin liquid for the classical spin model, Heisenberg model without any DM interactions. They also found us classical spin liquid with some pinch point. And we are going to look at it, this model with anisotropy as well as with DM interactions. And our conclusion, one of the conclusion is that these are unstable to DM interactions. So I have 10 minutes or so. 4 or 5 minutes. Okay, so now I'm going to apply our theory on this square Kagome. So we know that this is a dihedral group and you have n sides, so you'll have a 24-dimensional representations in a bracket and you'll have 5 irreducible representations. So there are too many informations here, I don't need all of them. So you'll have 5 irreps, 4 of them are 1-dimensional and this is 2-dimensional, and there is multiplets of each irreps which is here, that tells us that these irreps, 2 of them can mix each other, giving you a O2 order parameter and so on. And I also classify these 2 classes of irreps. One is the coplanar irreps and the other class will be the out of plane irreps, like ferro or antiferro, and they will give you some sort of a in-plane ferro antiferro or vortex or anti-vortex. That we'll see. Some of them we see is that, so these A1 or A2 are like vortices, but there are 2 sort of vortices, concentric vortex if you like, which is going like this, and the B irreps would be like anti-vortices. And the E classes are non-collinear FM or antiferromagnet, whereas these classes are out of plane ferro or antiferro. But one important point is that there are some irreps which does not satisfy the constraint. So that means if this irreps becomes the low energy irreps, what that would do is that it will not come by itself. It will try to scramble with other irreps. Okay, and then again we start with some generic Hamiltonian, and then we use this group theory, and what we found is that this is the Hamiltonian that is allowed, in which there is a DM interactions and there is this Heisenberg interactions with some anisotropy. And I write this Hamiltonian in a slightly complicated way, in which we sort of separated out these in-plane interactions and out of plane one, and we have only two parameters to tune. One is the DM interaction, another is the coplanar, this out of plane anisotropy. And I write this in-plane spin in terms of a theta, as you will see that will be useful later. And then we have this, should be able to diagonalize it, and all this out of or in-plane irreps, all this in-plane order parameter would be promoted by the DM interactions, and all the out of plane will be promoted by the anisotropy term. All right, so you do have, this is probably not important for us. And this is going to be the phase diagram for the antiferromagnetic case, and these are the 2 parameters, delta and D. And so let me focus on when the delta equal to 0. So that means you only have in-plane interaction. And it's sort of useful to write the spin in terms of the angle in the position space, and Q being the topological charge. And this is the helicity angle that will help us identify the vortex and anti-vortex phases. So defined is that as you put any DM interactions, you have either a vortex which form an ordering, or anti-vortex for if the DM interaction is the opposite way. And these are all the phases that we are going to find. I'm going to classify here. And what is interesting here is that these are 2 different topological charge, and the phase transition happens when DM interaction is 0, and this is where a spin liquid emerges. So this line gives you spin liquid. Okay, and the 3 sort of spin liquid we get. And this will be the spin liquid that is confirmed with the Monte Carlo simulation. And we also see that the spin liquids are of Coulomb phase type, which has been pinch point singularity. So let me classify these three types of spin liquid based on the group theory we have. So if you are at d equal to 0 and delta equal to 0, so you only have nearest neighbor interaction. So the theory has O2 spin liquid. So only those E-reps will scramble. So these are the E-reps that will sort of take random values and give you a degenerate manifold, which we called O2 spin liquid. And if you go to delta equal to 1, which is j equal to 1, so this is where your O3 symmetry will emerge. And you should be able to take a linear combination of all of them, and indeed that's what happens. We have confirmed with Monte Carlo, that's what we call it O3. And then you take the delta equal to infinity limit, so you do have this is the term in the Hamiltonian, and you'll have only Z2 spin liquid in which this Z2 order parameter will only take random values. So what we also find is that as we now turn on some DM interactions for a large anisotropic region, what we find is that, so both now starts competing. So we find is that this is the order parameter, which is the in-plane order parameter that still remains here as a uniform phase, whereas the out-of-plane one remains disorder. So that's what we call fragmented phase. Okay, and in fact, this fragmentation or the local structure of these vortices are something interesting. If you sort of go around it, you see that this is like a vortex, except that there is also an outer plane component which is like antiferro to each other. So that's what we call antiferromagnetic vortex. We know antiferromagnetic fermions, which was discovered last year, but I don't think anybody has talked about antiferromagnetic vortex. But this could be a kind of a simple example to look for it. And these are, so in plane is again order and outer plane is disorder. And we'll have some trivial phase, ferromagnetic phase, in which some collinear will come up, right? And I think 1 minute or maybe I'm done. So I think the instabilities are pretty obvious, and it should not be, so in a vortex phase, we'll have kind of a long wavelength of fluctuations giving you magnon, but because these are vortex topological, so you may expect some Chern number. And what is fascinating for us, which is probably what I'm going to look into later on, is that spin liquid comes as the phase boundary between two topologically distinct order phase. Okay, and we know that spin liquid is unstable to any sort of a finite DM interactions or even temperature. So with that I'm done, and I guess I can let you read this. Okay, thank you.
Let's all thank Tanmoy here. Thank you very much for the nice talk. Questions? Question? You have one?
So is the DM interaction allowed on both types of symmetry and equivalent bonds? Because you have the square bonds and the triangular bonds. Or is it only on one type? Or
no, this is the only one type of DM interaction that is allowed by the symmetry. First of all, we are starting at 2D.
Yeah, but there are two symmetry and equivalent bonds, the one on
Right.
the square, one on the triangle.
Right. So I think I have forgotten, but I think the DM interaction among the outer plane,
Yeah.
that is allowed. Now among this one of them, I forgot which one.
Okay.
You can check it later.
I see.
Because I mean, we have studied at 2D, if I have not mentioned, we have studied at 2D one. So inversion symmetry breaking allows, anyway.
More questions? No.
So this is my first talk on spin liquid. I have made it, may have made it very technical, which is not.
I have a small technical one.
Sorry.
So all of the description is strictly like 2D, right?
Right.
The material that you showed before that kind of realizes the same structure. Could you measure any similarities? Is there like the layers that are really that separated that you don't have in any like interlayer?
Right. So I forgot the numbers, but as long as the magnetization or the spin-spin interaction goes, I forgot the number, but the values the J values between them are substantially small. Actually on order of magnitude small. Maybe he can confirm. And electronically, these are not necessarily van der Waal. So whether you can separate them easily or not, that I do not know. But in terms of the spin degrees of freedom, the J is substantially small. So
Thank you.
for the spin model, this is.
So let's send Tanmoy again.